All right, so direct comparison test, basically what they want you to do with the direct comparison test is that you're going to be given a series and you're going to look at the sequence, so the a sub n part, right, the little formula inside, and you're going to see what other function you can compare it to in order to do something with it. So let me give you the theorem for this thing. So theorem 9.12. So this is the direct comparison test. Now, like I told you guys before, these are two, well, I'm not going to do both of them today, but this test is one of those that's kind of confusing to a lot of people. So make sure you kind of understand what's going on. It's not that the work is hard, it's just you have to understand why we do certain steps. Okay? The work isn't that difficult though. But here's the definition. So let me just write it out really quick. So let 0 be less than or equal to a sub n be less than or equal to b sub n for all n. Okay. Notice it's very important that you notice that a sub n is in the middle, b sub n is at the end. Okay. So note that a sub n goes in between the 0 and the b sub n. Now there's two situations. Situation number one, if the sum as n goes from 1 to infinity of b sub n converges, then the sum as n goes from 1 to infinity of a sub n converges. So let me explain this one. But go ahead and write it down. It says if the sum of b sub n converges, then the sum of a sub n converges. Now, what does it mean for a function to converge again? It goes to some number. So notice how a sub n is in between b sub n, right? So, and 0, sorry. So obviously the left side is a number. The right side we don't know, right? So I'm talking about this part right here. Okay? So the right side, the b sub n, we don't know yet. But if we know that the sum of b sub n converges, then what does that tell us about the sum of a sub n? So let me write this down. Yeah, remember the sandwich theorem? You guys remember that one from AB? It basically said if you can corner a function in the middle between two values, then it'll force that function to become something. It gets sandwiched in between. It forces it to do something. So look what happens here. So I'm just going to give you an example of what the first step means, okay? So if I take the sum as n goes from 1 to infinity of 0 and less than or equal to the sum as n goes from 1 to infinity of a sub n, which is less than or equal to the sum as n goes from 1 to infinity of b sub n. Let's say I do that. Okay? The left side is 0, right? Because if you just keep adding 0 forever, then it's 0. Then right here I still have the sum as n goes from 1 to infinity of a sub n. Now notice, let's take into account the first part of this definition. It says, what if the sum as n goes from 1 to infinity converges? So we call that big L, okay? Like some finite value. Well, if the sum of a sub n is stuck between 0, which is a number, and L, which is a number, can it be infinite? No, it's stuck between numbers. So therefore, it's forced to become a number itself. I don't know which number, but it's forced to converge as well, because it has to be stuck between two finite values. Does that make sense? Okay, so that's step one. Okay, step one is if the outer limit, the one on the right side, converges, then it forces the inner one to converge. Okay, again, I don't know what the answers are. We don't care. We just care, will it have a finite value? That's all. Okay, then there's step two. Step 2 is what happens if a sub n diverges. So if the sum as n goes from 1 to infinity of a sub n diverges, then the sum as n goes from 1 to infinity of b sub n diverges. So I'm going to do the same thing I did up here. Just to show you why this is the case, I'm going to start off the way I did the other one. Okay, I start off with the let statement. Let this be true. Okay, then I'm going to put in my sum. So let's, the sum as n goes from 1 to infinity of 0 less than or equal to the sum as n goes from 1 to infinity of a sub n less than or equal to the sum as n goes from 1 to infinity of b sub n. Again, we know the left side has to be 0, right? Because if you're just adding 0 over and over and over and over again forever, you're just going to get 0. What's the sum as n goes from 1 to infinity of a sub n if they say that it diverges? It's infinite, right? And then we don't know what happens to b sub n, but if the sum as n goes from 1 to infinity of b sub n has to be greater than or equal to infinity, then what must the sum of b sub n be? It must be infinite, right? So this must mean that this thing is going to infinity as well. So it diverges. Does that make sense? So they're forcing each other to have specific values. So if the middle diverges, the outer diverges. If the outer converges, the inner converges. Okay? Yeah.
Only when a sub n is less than or equal to b sub n?
Yes, and that's the key. You need your a sub n to be less than or equal to b sub n. Now, what exactly does that mean? Now this part I think is the easy part, the definition, but the hard part is how do we figure out what a sub n and b sub n are? So let me show you examples of that. And it's not that hard, but you do have to practice it a little bit. So let me just put, do these converge or diverge? So we'll start with this one right here. The sum as n goes from 1 to infinity of 1 over 2 plus 3 to the n. So the question here is that a sub n or is that b sub n, right? And we actually don't know until we start to compare it with stuff. So usually what you do is you say, okay, I have something that I can compare, or do I have something that I can compare this function to? Okay, so 1 over 2 plus 3 to the n. What function can I compare that to? All right, so this is what I'm going to do. I'm going to compare it with this function. Notice all I did was I got rid of the extra 2, right? The plus 2 part. So now look at those two functions. Which one's bigger? The one without the 2. Because the one with the 2 means that the denominator would be bigger. And if the denominator is bigger, it actually makes the function smaller. So that means that is the case, right? So that makes this part my a sub n, and this part is my b sub n. So here's the thing.
Why is that again?
Oh, it's because notice that they both have denominators, right? 2 plus 3 to the n. The other one is just 3 to the n, right? So the one on the left side, it has more adding to it. It's plus 2. So whatever the denominator is, the one on the left side has 2 more values, 2 more number values to it. So in other words, if you had a 1/10, the other one would be a 1/12. Now the bigger the denominator, the smaller the actual value is, right? So that's why we can say that that's true. Okay? Now here's the deal. You never check, okay? You never ever check your function. This is my function. That's the one I'm testing, right? you have to prove that this new function that you got, okay, you want to prove that that function either converges or diverges. Now, since that's my b sub n, what do I want to do with it? According to the definition, since I created a b sub n, what do I want to prove? That it converges, okay? I want to prove convergence because that's what I created. I created the b sub n. Sometimes I'll create the a sub n. It just depends. I don't know which one I create. I got to think of which functions to do and then apply them to my theorem. So what I'm going to do right now is I am going to do the proof that b sub n, or 1 over 3 to the n, I got to prove that it converges. Okay? Now, notice 1 over 3 to the n. Okay, 1 over 3 to the n. Does anybody know what kind of function or what kind of series that is? It's geometric. Yeah, it's 1/3 to the n. Right? My a value is 1. That's right here. But we don't see it, right? My a value is 1. My r value is 1/3. And if you remember your geometric series, if the absolute value of r is less than 1, then it converges. Is that what's happening with me? Yeah. So I can say that this 1 over 3 to the n converges by the geometric series test. Notice I didn't have to find my answer, okay? I didn't have to find the answer of what it converges to. I just want to prove that it converges. Now notice I'm putting a dashed box because that's not actually my answer. Now I actually get to put my answer down. This is just helpful for me to get my solution, because if b sub n converges, then what do I know about a sub n? It converges as well. Okay, and that's because of part 1 of the theorem. Go ahead. Yeah, you do.
Can you explain, like, why geometrically converge when there are values less than 1?
Oh, it's because if you consistently multiply by a denominator, by a fraction less than 1, anytime you multiply by a fraction less than 1, what does it do to any number? So let's think of, it makes it smaller, right? And what if you keep multiplying by that same fraction? What's going to happen to that number? It's going to eventually get smaller and smaller and smaller until eventually its size is what? Almost nothing. So that means it's going to stop adding to itself, which means it's going to converge eventually. Whenever, so if I get like the number 10 and multiply it times half, I get a 5, right?
Yeah.
And then that by half, I get 5 halves. That by half, 5 fourths. That by half, 5 eighths. Then 5 sixteenths. Then 5 32nds, 5 64ths, 5 1/28ths, right? The number's getting smaller and smaller and smaller and smaller. And you're adding these things up. You're getting every number that I've mentioned, you're adding it, adding it, adding it. So your number's getting bigger and bigger and bigger, but by small, small intervals, right? Well, if I keep doing that for the rest of my life, aren't I going to get to a point where my fraction is so small that it's no longer really moving the number up anymore?
Yeah.
So that means that it's reached a limit. It's converged. It's now at a specific point where it's no longer going to get any bigger or smaller, right? So we say it converges. That happens when your fraction is less than 1. Whereas if you multiply by 4/3, and then you get 10 times 4/3, that's 40/3, times 4/3, well, that's 169ths. The number's getting bigger and bigger and bigger. If you keep adding bigger numbers over and over, it's never going to converge. It's going to keep going towards infinity, right? So you want to make sure that the fraction is smaller than 1. That'll make it keep shrinking over time so that it converges.
And then what does the a value add to?
Well, the A value is just a constant that multiplies it. So the number still keeps getting smaller and smaller, but it just keeps multiplying by A every time. But it's still going to keep getting smaller over time. So your answer that you're going to want to write. So notice the thing that I just wrote right there, this is just like my check step. This is saying like, oh, look, I was able to prove that what I did actually worked and it converges. So then I got to say, since b sub n, which was the sum as n goes from 1 to infinity of 1 over 3 to the n converges, then a sub n, which is the sum as n goes from 1 to infinity of 1 over 2 plus 3 to the n, also converges. Now, I don't know if you guys heard Robert, but he said, like, do I have to write all that stuff? Honestly, I don't know for a fact that you need to write it all for your homework. I mean, if you understand what you're doing, then good, you understand what you're doing. But I would tell you on an AP exam, I would write it out because they want to know, like, how is it that you know? How do we know you're not just guessing? Right? How do we know that you know the work? So, for me, I would write, oh, look, that converges by the geometric series test. And since that converges by that geometric series test, then the other one converges. And actually, if you want to be really detailed, you can say by the direct comparison test. There's going to come a time, once we're done with section 9.6, where I'm going to expect you guys to always tell me which test you're using to prove it. Okay? Because if I just say, hey, questions 1 through 6, do these converge or diverge? You can literally just write converge, diverge, and get everything right without even knowing what you're doing. Right? It is possible if I'm giving you a 50-50 shot. Right? But if I tell you, okay, 50-50 chance you're going to get it right, but you must tell me which test you use, now it's going to show me that you understand what you're doing, because you're going to say, okay, well, this is probably geometric, so I got to do that. This is direct comparison, so I got to do that, so this is what I got. So, yeah, it is important you guys know which tests you're doing. Let me give you part B. So before I get to that, so notice I started off with the main function. I created another function, the b sub n. I tested b sub n for convergence because it's b sub n. Notice I didn't try to prove it was divergent. I tried to prove that it was convergent. Because if I prove that b is divergent, it doesn't force anything to happen. If a sub n has to go between 0 to infinity, it doesn't mean that it's infinite. It doesn't mean it's an actual number. So I got to prove convergence. Once I do that, then I can make my statement that it must converge. Okay? So let's do another one really quick. Part B. So from 1 to infinity, I want 1 over 2 plus radical n. So think about this one. What are you going to compare this with? So 1 over what? Radical n? All right, so I'm going to say I have 1 over 2 plus radical n, 1 over radical n. Which one is bigger? So yeah, so the 1 over radical n is actually bigger than the 1 over 2 plus radical n. So by the way, right now you're gonna see something interesting happen, but this is true so far, right? This is my a sub n, this is my b sub n, correct? All right, so if that's the case, then I don't want to test the 1 over 2 plus radical n because that's what's given to me. I want to test what I created. Now, I want to remind you guys that I can rewrite this as 1 over n to the half. What test can I use to test 1 over n to the half? P series. And what do I want b sub n to do when I test it? Converge, right? I want it to converge. So let's check it. The sum as n goes from 1 to infinity of 1 over n to the half. What does it do? This diverges. That's not what I want to prove. That didn't help me do anything. Okay, it's either convergence or nothing, right? Convergence or bust, right? So we have to say, okay, well, that test didn't work. That means that the b sub n choice that I picked wasn't great. Maybe I need to try a different function. So a lot of times what people say is, if that didn't work, why don't I just drop the power altogether? Let's just try 1 over n. So let's try this. I have 1 plus 2 radical n and 1 over n. Okay? So here's the question. Which one's bigger? Which one? 1 over? 1 over n? Well, the n would be bigger. So 1 over 2 plus rad n would be the bigger function. Okay, so that makes this b sub n and this a sub n. Are we okay with that? If you guys have trouble seeing this, you can do it algebraically to prove it, but an easier way is just graph them both and see which one is below the other, right? Just look for their heights. Which one's higher than the other? And you'll know, okay, that's my higher function. This is my lower function, right? And remember, just from 1 to infinity, don't look at the third and second quadrant. Just look at the first quadrant overall. So since a sub n now is the function that I created, what do I want to prove that a sub n does? I want to prove divergence. Notice step 2 from your direct comparison. It says, if the sum of a sub n diverges, then b sub n will diverge as well, right? And you're always testing the one you created. So what happens with 1 over n? You guys agree that we should do p-series for this? Yeah, what's my p-value? 1. And if p is equal to 1, what happens with the p-series? It diverges. This diverges by p-series. And that's perfect. Because if that diverges by p-series, that means a sub n diverges. And if a sub n diverges, what happens to b sub n? It must diverge as well, right? So I'm just going to write that down. Since a sub n, the sum as n goes from 1 to infinity, from 1 over n, diverges by p-series, then b sub n from 1 to infinity of 1 over 2 plus radical n also diverges by direct comparison test. Now, so that's basically it for the lesson. I do want to kind of talk to you guys a little bit about this, though. I always get people that ask me, how do I know which function I need to use? That's the hard part. You don't. You just try stuff. You truncate a number from the bottom and use the highest degree in a denominator and see if that works. And if it does what you wanted to do, great. But if it doesn't, maybe remove a power, okay? And maybe that'll work. But it's kind of like a guessing game. And this is why a lot of people don't like direct and limit comparison tests, because it's up to you to decide, what am I going to use? Okay, so it's on you. There is no trick. The easiest trick I can tell you is just to get rid of the excess weight in the denominator and just use your degree. Okay?
How would pop up as a question on the test?
Sorry?
Like on the AP test, how would it pop up as a question? Like, what would they ask you?
Honestly, the only times I've ever seen these types of questions on an AP exam, I think, have been in the multiple choice sections. So it'll kind of look like this. Check for convergence, that type of stuff. So, all right, let me give you guys a homework for this section. Or you know what? Let me wait on that. I'll include it in the notes, okay? It's not going to be in the video, but it'll be in the notes.